Let's get started. This lecture is going to be about steel structures. It is the first of a series of 3 lectures on steel buildings, steel frame buildings. Before we start, I would like to backtrack to the precast concrete lecture, the previous lecture, where we talked about the office buildings in Australia, which used precast single Ts, where the architect manipulated the shape of the T to make these uh, rather handsome profiled ceilings in the office spaces. This is a building in the UK, an office building that has been constructed recently that uses exactly the same system. So we have a precast single T that has been manipulated so that the stem of the T is narrow and tall in the middle of the span where the bending is the greatest, and then the stem becomes shorter and fatter and wider at each end of the span, which produces then these oval recesses in the ceiling, or in the soffit. So you can see that this architect is also incorporating uplighting and downlighting in these oval recesses so that the workers get reflected light onto their workplaces. And in this case, the concrete structure has been painted white. You can see it during the construction. So you get the sense very much here that in the center of the span, the legs of the T's are much deeper, and then they get shorter and fatter and wider toward the end of the span. So this also produces a slightly dished or curved soffit to the underside of the concrete slab. This is the section of the building, so you see in the section that curved underbelly to the soffit, and then you see the precast single Ts. The services are delivered here through a raised floor that sits on top of the single Ts. And there are 2 long bars of offices on either side of the building with an atrium in the middle. The atrium has its own structure, which is steel, and so there are 3-story high steel columns and a glazed roof over the atrium. So we have 2 precast concrete structures on either side, and then a steel frame structure in the atrium. The photograph on the right is within the atrium, so you see the slender, tall steel columns with then the 2 precast concrete office buildings on either side. And you see the plan organization below. So you can see that the vertical cores are organized very rationally in 3 bands of the building. And the 2 long sides of the building will be the office facades, and you can see at the right hand end of the building in the drawing the restaurant, and you'll see that has the facade of that in a moment. The office wings have exterior horizontal sun shading, which is suspended from above on very slender cables, and the restaurant, which faces south and is next to a pond, has a very deep overhanging roof with louvers to shade the fully glazed facade. So the architects here are thinking about structures. They're thinking about solar shading and how to make solar shading part of the architecture. And they're also thinking about how the structure can contribute to the spatial character of the building. This is an example of what you might call a performance section drawing, in which you see here integrated structure and services. So the structure here is precast concrete elements that in square structural bays that form these pyramid spaces now in each square bay, rather than the recessed ellipses that we saw before. So now we have these pyramidal recesses in the ceiling, and the space between these ceiling elements and the floors above then are fully occupied by ducts and services. And you can see that there are also planted roofs and planted terraces in this building. So this is telling us about the integration of structure and services in this project. As your work progresses in the semester, I'm hopeful that you might be doing drawings like this to show your intentions. Okay, so that brings us then to the beginning of the first steel lecture. So when we talked about concrete, we talked about it as a very old material used by the Romans, which then disappeared for about 2,000 years and reappeared at the end of the 19th century and became very closely associated with the development of modernism in architecture. We saw that concrete has the potential to be either stereotomic, as these two images show, the dome of the Pantheon on the left and the Pheno Science Center by Zaha Hadid on the right, or it can be used tectonically as a frame. And so we see on the left Le Corbusier's intentions in 1920, showing the tectonic character of the concrete frame. And on the right, the Louis Kahn precast concrete two-way structure. Both are examples of how concrete can be used tectonically. Another construction material closely associated with modernism is steel. And steel, unlike concrete, which was very old, used by the Romans, steel really is a new material, a relatively modern material that appeared in the mid-1800s and transformed architecture. It transformed both the ability to span and the ability to build up into the sky, to build high. And so on the left, you see the Brooklyn Bridge, which is an outstanding example of the spanning capability of steel. There's this beautiful contrast in the Brooklyn Bridge between the heavy compressive masonry towers and the cables and cable supported bridge that spans between the towers. So between compression in the towers and tension in the cables, which are very light and delicate indeed. And on the right, you see the Guarantee Building in downtown Buffalo, which is an early example of a steel-framed skyscraper. So for us today, this does not seem like a tall building, but at the time, it was a very tall building, and as we know, was the stepping stone to much taller buildings. So unlike concrete, and on the left you see the skyline of Chicago, which really is shows the history of the development of the skyscraper from 10, 12 stories up to 115 stories tall. Unlike concrete, which can be used stereotomically or tectonically, steel really is used almost exclusively in the tectonic realm, where we're using linear components to make space. And what you see on the right is the roof of the British Museum, which is a very delicate steel-framed roof with a very long span. So steel is a metal, clearly. It's not a pure metal that we dig up from the ground. It is a man-made mix of elements, which we call alloys in steel, and it is a mix of iron and carbon. So alloying steel is not new. The Model T Ford apparently contained 50 different alloys of steel, each one designed for particular level of strength and performance in the automobile. In terms of sustainability, steel has many minuses and it has a few pluses. So on the minus side, the manufacture of steel is very damaging to the environment. We have to mine iron ore. This causes damage to the surface of the earth. We require large amounts of fossil fuels and water to make steel. It requires very high temperatures to make steel, and this production process produces a lot of pollution. And the image that you see on the right is similar to when you drive from Buffalo to Toronto. You get to Hamilton, and the steel works there is still in operation and is churning out smoke and probably some pollution still into the atmosphere, even though it's much cleaner than steel manufacturing used to be. In terms of life cycle costing of buildings, steel, another negative is that steel cannot contribute to the environmental performance of the building in the same way as concrete. Steel does not have any thermal mass. On the plus side of the equation, steel can have a much lower embodied energy, and particularly the steel that we use for buildings. Most of it is recycled. 2/3 of all the steel used made for building construction comes from recycled metal. And steel can be recycled multiple times without losing any of its qualities, its structural qualities. So using recycled steel requires less fossil fuel, less heat, less water, and this reduces the embodied energy of steel significantly. Also on the plus side is steel gives better performance per pound than concrete. Steel is lighter in weight than concrete for the same job. So if we have to span 30 feet, we can do it with a steel beam, which will weigh less than a concrete beam for the same span. At present, the most widely used steel for building structures is called mild steel. And this is an alloy that has been designed to maximize the structural performance of the steel to give the right mix of workability and stiffness and strength. Most structural steel, as I said, is produced from recycled scrap metal, and a steel mill, for example, might go through 300,000 recycled cars per year. The production process for mild steel or structural steel used in buildings is called hot rolling. And this is the image you see on the bottom. So the element in the bottom right of the picture is a heated ingot of steel that's heated to white hot, which is then run through a series of rollers to produce structurally efficient shapes. So that's why with hot rolled steel sections, you often see radiused corners because it's been produced through rolling. The most common and widely used shape is what we call the W section, the wide flange section. So our slang for this is I-beam, but its proper construction name is W section for wide flange. And wide flange beams come in many shapes and sizes, but in two, broadly speaking, two proportions. So the top left drawing is the proportion that you will find for beams, where the W section is relatively narrow and quite deep. And then the second drawing, which is what we call an H column, is if you drew an outline around it, is much more square in proportion. So the tall, narrow W section is for beams, and the H section is for columns. So this would be a beam section. So W sections are identified with the prefix W and then two numbers. So we might have a W 12 by 14. And this means that the W section is nominally 12 inches tall and it weighs 14 pounds per foot. W12s will come in many different weights, ranging from 14 pounds per foot to 336 pounds per foot. And so to achieve 336 pounds per foot, the webs and the flanges will end up being much thicker. So why is weight important for a steel section? Two reasons. One is the weight affects the structural performance of the steel section. So obviously heavier sections are stronger structurally. And the second reason is cost. So steel is costed by its weight. We don't buy wood by weight. We don't buy bricks and blocks by weight, but steel is costed by its weight. So W12s or any W section is made in a series of different weights so that the structural engineers can always choose the lightest section possible for the particular structural work that has to be done in the building. The actual and nominal dimensions of steel sections are different. I can't give you a rule of thumb. You have to check the steel tables. So for example, a W12 by 14 is actually about 12 inches deep from top to bottom. A W12 by 336 is 17 inches deep, so that's 5 inches deeper. Both are W12s, but the increased thickness of the flanges increases the size of the W section. So there are no rules here. You have to look at the steel tables to understand the actual dimensions. If you are drawing the Conibear shell house, you can simply, if it says W12, you can draw it at 12 inches deep. We're not going to check the steel tables. The maximum depth for a standard rolled steel section is about 40 inches. So W36s, the heavier weights, will be about 40 inches deep. Other common steel sections are angles. These have the prefix L. And so we can have equal angles or unequal angles. The table on the right you can see is an L9 by 4 by 1. And the 9 by 4 is the length of the two legs of the angles, and then the third number is the thickness of the elements. So 1 inch thick is obviously heavier duty, but we can also get it down to ½ inch thick. Or we can have channels, and these have a C prefix, and these are designated in the same way as W sections. So this would be a C15 by 50, would be nominally 15 inches tall by 50, weighing 50 pounds per foot. And you can see that each of these channels is made in different weights. Another common steel section is tubular sections. So these might be designated by the prefix HSS, which is hollow steel section, or by TS, which is tubular section. So the square tubes that you see on the left would be TS, for example, 5 by 5 by 1/2. So the 5 by 5 is the inches, this is 5 inches square, and the walls of the tube are a ½ inch thick. If it is a TS5 by 1/2, that means it's a circular tube that is 5 inches diameter with a ½ inch thick wall. So if we are using standard W sections, then the typical maximum rule of span, absolutely standard steel structure, is around 36 feet. So you could have 36-foot square structural bays, and you would be pretty standard steel structure. The rule of thumb for the depth of beams is 1/20th of the span. So if I have a span of 20 feet, my beam is 1 foot deep. So if we want to go over 36-foot spans, we need structural members that can do that. And there are many different ways of doing this, some of which we already know about. So the first are open web steel joists or steel bar joists. As you remember, we talked about these before the break. And these can be up to 48 inches deep, standard production, and can span up to 60 feet. What you see in both of these images are what we would call one-way systems, in which all the trusses go in one direction. We could also use open web steel joists in two-way systems, where we run these trusses in two directions, which is what you see here. That is not the same as this, which is a continuously triangulated thick plane, and it's continuously triangulated in both directions. And so the depth of this plane is probably about 8 feet. You can see that the worker can stand in the depth of the structure. You can see that the structural elements are very slender. And this forms an extremely stiff structure that can span up to 150 feet. And so this is called a space frame, the continuously triangulated surface. So this is it in its simple planar form. This is also a space frame. So this is a building in Kazakhstan by Zaha Hadid Architects. And the blue structure that you see here is a thick surface, again, probably 6 to 8 feet thick, continuously triangulated in all directions, made up of very delicate members that can span quite large distances, in this case, curves, without any intermediate support. And here you see another image of that project under construction. So you can see here that there is a site cast concrete core. Then there is a steel frame made of W sections built around that core, and some of the W sections are curved in profile. And then the steel space frame obviously defines an outer envelope for the building. Another way of increasing the spanning capability of steel is to make castellated beams. So at the top you can see a standard W section that is cut in the shop to a zigzag profile. The two pieces are taken apart, and then the top piece is slid so that it can be placed on the bottom piece and re-welded. So now what we get is a deeper structural section with no additional weight and also no waste. So castellated beams are a good way of getting a deeper structure, and this would also enable us to pass services through these openings. Also now you can get what are called cellular steel beams. These are manufactured this way. It's a standard product. So these are W sections with the holes already cut out. And these are made so that we can pass services through the structure in the same depth as the steel beams. So with steel structures or concrete structures, anytime you want to make a big hole in the structure for something like an air duct, your structural engineer is going to get rather nervous and is going to limit what you can do. So something like these, the castellated or the cellular beams or the castellated beams, mean that we can freely run services through these holes. Then stepping it up a notch to do even larger structures, we can do welded plate steel components. So these are not hot rolled steel sections. These are much larger, and these are all made by welding together steel plate to make, for example, bridge girders or highway bridge or railway bridge structures. And you can see that this girder that's being lifted into place has all the holes for services pre-cut in it, prefabricated, and can simply be craned into place. So and we can make columns this way. So the box girder on the top could be a beam. If it were square in proportion, more square-ish in proportion, it could be a column. And beams and girders. So an example of this, where steel plate structure, is the Sears Tower in Chicago, which was the original name of this building. It is now called the Willis Tower. And it is 110 stories tall, so it's one of the super tall skyscrapers. It was the tallest building in the world for about 20 years. The columns are welded plate I sections, and the beams are as well. And at the top of the tower, the plate is 1 inch thick, and at the base of the tower, the plate is 4 inches thick solid steel. So as the loads come down the building, the steel structure has to thicken in the same way that we saw with the Monadnock brick walls getting thicker, only now this all happens within the steel structure and it is not visible in the finished building. So these are custom fabricated steel components welded together from steel plate. They are not standard hot rolled sections. So how do these components get combined together into systems? Just like concrete, we can have one-way systems or two-way systems. In the one-way systems that you see pictured at the top of the drawing, we get beams going only in one direction. And in the bottom drawing, you can see that we have beams running in two different directions. The most common floor system used with steel frame structures is to use a corrugated steel deck uh, as permanent formwork for pouring a site cast concrete slab. And the value of this is pictured in the image on the left. If we have a thin sheet of galvanized steel, as you see at the top, it's floppy. It doesn't have any structural spanning capacity, but when we corrugate it, it becomes very stiff, and it's still just a thin piece of galvanized steel, so it's very light in weight. But it can span, and it becomes the permanent formwork then for a site cast concrete slab. So those of you who are drawing the Conibear shell house, this is the floor system that you have in the building. And so here you see a steel beam. You see the corrugated steel deck sitting on top of the beam. And welded to the top of the beam are shear studs, those vertical studs that you see projecting through holes that will be drilled in the corrugated deck. And then once the concrete is poured, it bonds to those shear studs, and that makes the building into a rigid diaphragm. The image on the left just shows that there are hundreds of different profiles of corrugated steel deck. This formwork then is not stripped away when the concrete cures. It remains in place, that's why we call it permanent formwork. So here you can see a steel frame being erected, and you can see that the shear studs they've been welded onto the steel beams in the workshop before they come to site, and the corrugated steel deck is going to, those are going to project through the corrugated steel deck and bond with the concrete. And that will make then all of the floors rigid horizontal diaphragms to help brace the building. Another way that we could make floors with a steel frame would be with precast concrete planks. So in this slide, you see concrete columns and beams. These could easily be steel columns and beams. And then we could have precast concrete floor planks to make our floor. But this is much less common with steel frame, but it is possible. So how do we join members of steel together? There are three typical methods, and your structural engineer will decide. This is the method that was originally used historically and is not widely used now because it's very labor intensive and expensive. So this is the rivet process, in which cylinders of steel are fabricated with a domed head at one end, which is what you see on the left. These are heated up on site until they are very hot, not molten, but hot, and then they are placed in pre-drilled holes, and with a pneumatic hammer on site, the other end is hammered into a domed head. And then the steel rivet cools, and it shrinks, and it makes a very, very tight joint. So you can see here why this is such a labor-intensive process. And but the old railway and road bridges that have these domed heads on them, these are all rivet connections. And in fact, rivets were used up until World War II, and it was only after World War II that welding and bolting came in and replaced riveting as a method of joining steel. So on the left, we see bolted connections. These are very fast, very inexpensive, and typically because the steel frame is hidden away or concealed in the finished building, your structural engineer can design these connections. If the steel is visible in the finished building, you as an architect might want to have more of a say about what these connections look like, or you might specify that the connections be welded, which is what you see on the right. And this is literally where two pieces of steel are fused together with molten material. So there are no bolts here, there are no dome heads, simply two pieces of steel fused together. This is obviously a highly skilled trade, very expensive, and it depends on your aesthetic. So I apologize for that interruption. The phone rang. So we were talking about the three ways of making connections for the steel frame. Frames have to be braced in all three axes, the two vertical axes and the horizontal floor slabs. And there are various ways of doing this. So the top left-hand image shows diagonal bracing of a steel frame in all three axes. And I would say that this is overdone. You do not need to diagonally brace every single bay of a floor structure or every single bay of an exterior elevation. You can brace one bay at each end of the building and you would be fine. The bottom image on the left shows the same thing, but all with site cast concrete, providing shear walls and shear planes, rigid horizontal diaphragms in all three directions. And the third image shows a mix of diagonally braced steel cores with the rigid concrete horizontal planes, floor planes. So we can use all steel, we can use all concrete, or we can mix steel and concrete together. But the most common method of doing this is this, where we have site cast concrete cores, and those are built first because site cast concrete is a wet trade, and these are going to provide the lateral stability in two axes, and then we build a steel frame around those cores and provide rigid horizontal diaphragms in the floor structure of the steel with site cast concrete slabs. So that's the most common in our North American construction culture. So in order to make a building rigid, typically what we do is we brace the cores because we know that these go continuously from the top of the building to the ground. So they're logical places to provide lateral stability. And this strategy of bracing the cores is good for buildings up to about 60 stories. But if we want to go higher than that, we have to move the bracing out to the perimeter of the building to get a larger cross-section of rigidity. And so, for example, this is the Hancock Building in Chicago, which is another one of these 100 stories plus buildings. And you can see that the diagonal bracing now is around the entire perimeter of the building. So the cores now are not stiff, but the entire perimeter of this tower is diagonally braced. On the right, you see the construction photo, and on the left, you see the finished building with the diagonal bracing part of the cladding. The San Francisco Federal Building that we talked about in the last lecture uses both strategies. And so the red lines here show that both the central core and the two intermediate cores are shear walls. And then the east and west end facades are also shear walls. So it's using a combination of bracing through the cores and perimeter bracing. So when we design a steel structure, your structural engineer will do a set of drawings of the steel frame structure. And then those drawings go to the steel fabricators, who will in turn do a set of shop drawings. And the shop drawings are the fabrication drawings. They're much more detailed. They show every hole, every bolt, every plate that gets welded in, all of the profiles of the welds. Every single detail is drawn and specified. The shop drawings then come back to the design team, the architect and the structural engineer, who have to review them and approve them for fabrication. And so, as an architect, you can either approve the drawings for fabrication or approve them provided the changes that are noted or redlined on the drawings are incorporated, or if substantial changes are required, you can refuse to approve the drawings and require them to be amended and resubmitted for approval. So because steel is a highly skilled trade, as much prefabrication as possible is done in the workshop. And this is what you see on the left. This is much easier than doing the work 80 stories up above the ground. And the limit to the size of elements that can be prefabricated is based on, determined by the method of transportation from the workshop to the building site. And so if you're transporting by truck, you obviously have rules about maximum sizes of loads on the highway. If you're transporting by ship or by train, you will have different dimensional constraints to work to. So if we look at the Sears Tower again, we can understand, we will see how these elements were prefabricated. And so to achieve 110 stories in height, the structural concept of this building is called bundled tubes. And so there are 9 tubes that are bundled together to make a square. And each one of those is structurally rigid. And then as you go up the building, all 9 tubes are present on the lower floors of the building near the ground. And as the building ascends, the tubes disappear so that at the top there are only 2 tubes remaining. So basically the building is tapering from ground to roof. So that's what you see here in this image. So these drawings then show that section AA is at ground level, where all 9 structural tubes, which each one is rigid in itself, and then the whole bundle is rigid around the perimeter. And then as you go up the building, tubes disappear until you have only 2 left at the top. You also see in this drawing the slightly darker bands around the tubes, which are diagonally braced belts, let's call them. And these are providing stiffness to the tubes. Literally, they're like belts at 30-story intervals. So there's no diagonal bracing between those belts, only verticals and horizontals. And then those belts are 2-story high spaces with louvers, which you see in the right-hand image, and these are the mechanical plant rooms. And so each mechanical plant room serves down 15 stories and up 15 stories. So this belted structure is performing both structurally and in terms of the delivery of mechanical services. So here you can see the louvers on the facade for the belted structures. So here then you see the frame under construction, you see the verticals and horizontals, and at the top of the construction is one of those heavily diagonally braced belted zones where the mechanical plant is, and this one actually looks as if it's 3 stories tall. So here is that structure again. These are the custom fabricated I sections where the steel is 1 inch thick at the top of the building and 4 inches thick at the ground. And these are the prefabricated elements. So it's prefabricated in 2-story segments. So each horizontal that you see in the element to the right on the crane is a floor level. So these are 2-story high segments. And then the joints between the elements vertically is made about 4 feet above the floor, not at the floor level. This is to simplify the joint. And then the joints horizontally are also made at midspan rather than where the column and beam come together. Again, this simplifies the joint. So these are prefabricated in 2-story high elements. This is just to show you that when the building was completely refurbished about 5 years ago, the building was built in the 70s, and it was single glazed and consumed a huge amount of energy. And so about 5 years ago, they completely stripped the building down to the structure, put on an entirely new glazed envelope, which is now double glazed, very high thermal performance, replaced all the services of the building, etc. And at the top of the building is this observation deck. So this is 110 stories above the ground, and it is a frameless glass cantilevered structure. So then here you see the completed building with the glazed skin, the belts around the 9 tubes or around the tubes, and the mechanical plant rooms in those zones. So while steel is a very strong and stiff and high-performing structural material relative to other materials, it is not a perfect material. Like all construction materials, it has drawbacks. And so it has a couple of significant weaknesses. One is that it rusts. So it corrodes when it's exposed to moisture. So we have to protect it from moisture. And this can be done in 2 ways. Lighter weight components and small components are protected from moisture, as you see on the left, by dipping them into a bath of molten zinc. And this is called galvanizing. And more heavy-duty, larger-scale elements are protected with the dark red or colored paint that you see in the right-hand image, which is protecting them against moisture. And so in the image on the right, the dark red elements are the primary steel structure. They're protected with paint. And then the infill elements are light gauge steel studs, and these are all galvanized. The second big weakness of steel is that it has to be protected from fire. So it doesn't burn in the event of fire, but the heat from a fire can weaken the steel to the point that it fails structurally or deforms to trigger a collapse, a building collapse. So in the image on the left is one of Mies van der Rohe's office towers in Chicago, and he very much wanted to express the steel H-section columns at the corner of the building, which you see in the plan, but he, like every other architect, had to protect these columns from fire. And so what the image shows is 2 different ways of doing this. On the outside of the steel section, they are encased in site-cast concrete, which is what you see in the photograph and also in the drawing. And then inside the building, that same column is encased with expanded metal and wet plaster. The little eye sections that you see at the window mullions that go vertically up the face of the building are only stiffening the curtain wall glazing. They are not holding the building up, and therefore they do not have to be fire protected. So we can encase steel columns and beams in concrete, or as Mies did on the interior of his building, we can wrap them with expanded metal and wet plaster. So here you see an H-shaped squarish column wrapped in expanded metal and plaster. We can wrap a steel column and beam in layers of drywall or gypsum board, and clearly the greater the fire resistance needed, the more layers that you have. So we should talk about fire resistance. Fire resistance is expressed, the purpose of protecting structural elements from fire is not to protect the building or the real estate itself. The purpose is for life safety. So to allow enough time for the building to be evacuated before it collapses. And so fire protection is expressed in terms of time. You can have half-hour rated fire protection, 1 hour, 2 hour, or 4 hour fire rated protection. So clearly half-hour would have, in this particular case, fewer layers of drywall, and 4 hour fire protection would require more layers of drywall. So understanding this, the thing about the time and the thickness of the fire protection applies to all of these methods of fire protecting. So in the Hancock building in Chicago, you see the steel frame on the right, and you see it's painted that dark red to protect it from moisture. And then on the 3 stories at ground level, you can see the steel structure has been wrapped in a white blanket of material, a fire-rated material. So we can wrap it with a fire-rated blanket. That's another method. The most common method of fire protecting steel is spray-on protection. And this looks like oatmeal sprayed onto the building. Again, different thicknesses yield different fire protection ranging from half-hour to 4 hour. This is not something you want to see in the finished building, so it has to be covered up with cladding. So the building that you see constructed on the right, where you see the steel sprayed with fire protection, will be covered with metal cladding. Another method of fire protecting steel is shown in this image, where the structure is now exoskeletal, meaning it is outside the skin of the building. And this structure is actually supporting the floors of the building. So each time you see the projecting dot on the diagonal grid, that is a connection to the floor structure. So in this particular case, the exoskeleton is made of stainless steel tubes, which are filled with water with antifreeze in it. So the water keeps the tubes cool in the event of fire. So water-filled structures are very unusual. They're quite expensive to build. You would have to use stainless steel so that the steel doesn't corrode away. This image also shows another strategy that could be used, which would be not to have a water-filled structure, but to design the glazed envelope of the building to have the fire rating, and this then would be a flame shield to protect the exterior structure from the fire inside. And the final method of fire protecting steel, which I don't have an image for, is intumescent paint. So this is a special kind of paint that when there is a fire, it foams up and the foam forms a thick protective layer around the steel element. So we can encase steel in concrete, we can wrap it with expanded metal and wet plaster, we can wrap it with gypsum board or drywall, we can spray on fireproofing, we could have a water-filled structure, we could design a flame shield, or we could use intumescent paint. So this shows a steel frame being erected on the building site. And what you can see here, or what I should explain, is that the columns are continuous and the beams are interrupted. And so the columns are continuous from ground to roof, and the beams come to the columns. The columns come to site in approximately 2-story high lengths, which are then spliced together on the building site. And you can see in this image that the columns at the lower part of the frame that's visible are a heavier duty section, and that at the splice it changes to a lighter duty section at the top of the building. And so when the steel structure comes to the site, each column will have a steel base plate welded to it with holes drilled so that the bolts that have been cast into the foundation can project up through those holes, and it gets bolted to the foundation. The steel plate does not sit directly on the concrete foundation. It is shims are placed under the base plate to hold it about an inch up, so that the entire steel frame can be precisely leveled across the building site. And once that is done, then that 1-inch space is grouted in. What you see on the right is a typical bolted connection in which the column is continuous and the beam comes to the column, as I said. The column splices, which you see in this image, are not at floor level. They are not where the column and beam joints are. They're about 4 feet above floor level. This is much easier for the workers, and they don't have to make this connection on their hands and knees. And it's much less complicated because you're not dealing with the column and beam connection. There are several different ways of doing column splices. The image on the left, if both of your steel sections are the same size and weight, then you can simply bolt a splicing plate on the outside. The image on the right, if you're changing from a heavier section to a lighter section, then you will need a shim plus the plate. The shim fills the gap between the lighter duty section, and this all gets bolted together. And then if you have a much more significant change of section, you might need to do something like this, with a weld on top of the heavier section, and then an angle welded to that plate and bolted to the column. So there are many different ways of doing column splices. And finally, composite columns. So this is where we might have a steel tube as a column, and we can fill it with concrete or concrete and reinforcement. So in these drawings, I apologize that they're a bit fuzzy, but they were the best I could find. The red lines represent steel tubes, either circular or square or rectangular, that have been filled then with concrete. If we want even heavier duty structural performance, we can put rebar inside the steel tubes and fill them with concrete. So the advantage of this is if you have a multi-story building and you want to see your steel columns and you don't want to use spray on fireproofing or have to clad them and hide them away, concrete inside the steel tube provides fire resistance, is deemed to provide the fire resistance. So this is a very good thing if you want to see the steel tube. Also, if you use these composite structures with steel and concrete together, then you can get very strong and stiff columns that are very slender. This is good particularly if you have quite tall columns that are unrestrained and you want them to be slender. Okay, that finishes the lecture for today. Thank you very much.